All right, let's jump into another deep dive. Today, we're tackling a connection
Yeah.
that's going to make you stop and think, hold on, how is that even possible? We're talking combinatorics, the
Right.
math of counting and arranging things, and how it might just be a
Right.
key to understanding the building blocks of the entire universe.
It really makes you think, doesn't it?
Mm.
That simple counting could be
Yeah,
so fundamental to how reality works.
absolutely. The paper we're looking at today is titled Deriving the Quanta of the Standard Model from Simple Combinatorics, and it really dives deep into this idea. The author kind of blends ancient philosophy with modern physics to make their case.
You know, it might surprise you, but they actually start with ancient philosophers.
Oh, really?
Yeah, like Plato and Aristotle and their ideas about forms and dualities.
Hmm.
Then they bring in Hindu cosmology, specifically Brahma Chakra, which is the cycle of creation and destruction, and the three gunas, representing different types of energy.
It's like a history and philosophy lesson all rolled into one.
Yeah.
But how do they tie these ancient ideas?
Right. To modern physics.
Yeah.
Like, how does it connect to our understanding of the universe at the smallest level?
That's where the combinatorics comes in. The author connects those three, guna, sattvaguna, rajaguna, and tamaguna, to the variables we use in combinatorial calculations, n, k, and c.
Okay.
So n is the total number of elements in a set and corresponds to tamaguna, the static quality. Then k is the number of elements we're choosing for subsets, and that reflects rajaguna, the mutable nature.
Hmm.
And then you have c, the number of possible subsets, which embodies sattvaguna, the sentient quality.
I think I'm following so far,
Mm-hmm.
but it's still a bit abstract. How do these variables, which are connected to ancient philosophies, actually relate to the physical universe? I think the author uses a really interesting analogy to try to explain this, right?
Exactly. They use the analogy of a rainstorm, which might seem kind of out of left field, but it really helps visualize these abstract ideas.
Okay, I love a good analogy. Let's hear it.
All right. So imagine a rainstorm. The first phase, the sattvaguna phase, is like when the clouds are forming.
We can count those clouds. They're like the subsets.
Right.
But we can't actually see the individual water droplets within them. Like, we can't count the individual elements yet.
Okay, got it. So the clouds represent the subsets, the C variable, but the individual elements, the water droplets, are still hidden.
Exactly. Now, as the rain starts falling, that's when you enter the Rajaguna phase.
Okay.
The author compares this to the sound of raindrops hitting a window. Each tap is an element being counted within a subset, so that's like the K variable.
Yeah.
Hear the rhythm, you can count the taps, but you can't tell one raindrop from another.
I love that. It really illustrates the point. Each tap on the window is like counting those elements in a subset.
Yeah.
But what about the tamaguna phase? How does the rainstorm analogy work there?
All right, so imagine the rainstorm has ended, and you're left with hailstones scattered on the ground.
Okay.
Now, each hailstone is distinct and countable, just like the elements in the original set. That's our N, the total number of elements, becoming tangible. It's like the universe solidifying in a way.
Wow, that analogy really brings it to life. It's like the universe goes through these different phases of counting and differentiating, starting from a state where the individual elements are hidden and then moving toward a state where everything is distinct and countable.
It's a fascinating way to think about the process of creation, right? Like the universe is constantly counting and rearranging itself.
It definitely makes you think about it differently. But the paper doesn't stop there. It also says that at its core, the universe is based on unity, on oneness. Can you elaborate on that a little?
Sure. The author suggests that this oneness is present right from the beginning in that undifferentiated cosmic set, and then it gets transferred to those individual elements through this process of differentiation we were just talking about. So everything starts as one and then separates into those distinct parts, but each part still carries that connection to that original unity.
This is where things start to get really interesting. The author also highlights the role of emptiness. Now, this seems a little counterintuitive. How can emptiness be crucial to the creation of, well, everything?
That's a great question, and it's really key to the author's whole argument. They propose that a single subset containing 0 elements, which is represented by RA area 0, is absolutely essential.
Yep.
The subset represents that empty state, that void that comes before the Big Bang.
Yeah.
And it's from this void that the universe emerges.
So you're saying you need that zero, that nothingness, to actually kickstart the whole process of creation.
Exactly. It's like the universe needs that blank slate, that empty canvas, to begin its combinatorial game.
Okay, I'm starting to see how the author is weaving these ideas together. But how does this void lead to the creation of the particles that make up our universe? I mean, we know the universe is made of matter, and matter has its opposite, antimatter. How does that fit into this whole picture?
Well, that's where things get even more mind-bending. The author suggests that this RU subset, the void, is what allows for those two sets of particles that are basically mirror images of each other, matter and antimatter.
Okay.
It's like that void splits into these two opposing forces, each containing the potential for all those particles that we know and love. They're mutually negating, meaning they have opposite charges, but together they co-create the universe.
So it's like the universe needs both something and nothing to exist. They define each other. And this duality, this interplay of opposites, is what sets the stage for everything else that follows.
Exactly. It's such a fascinating concept, and it's really just the beginning of what the author explores.
This is already blowing my mind.
Yeah.
But before we get to how these ideas connect to the actual particles of the standard model, there's one more thing I want to touch on: modulus math. The author brings this up, and it seems like an even deeper layer to this whole combinatorial view of the universe. Can you explain what modulus math is and how it relates to the author's argument?
Absolutely. Modulus math, you might remember this from school.
Yeah.
It's basically the math of remainders.
Okay.
The author focuses on base 10, modulus math, and this idea that 0 and 9 are equivalent in this system.
I vaguely remember that. If you keep dividing a number by 9, the remainder will always be between 0 and 8, so 9 essentially acts like 0 in that system. But how does that relate to the universe?
The author connects that cyclical nature of modulus math to the cyclical nature of creation itself. They suggest that 0 and 9, in this context, represent those empty and full states of creation. It's like the universe is expanding from emptiness, reaching a state of fullness, and then potentially collapsing back into itself, only to begin the cycle all over again.
Wow. So the very structure of numbers, the way they wrap around on themselves, might actually reflect the cyclical nature of the universe. That's a pretty mind-blowing concept. And it makes me wonder what other hidden patterns we might find if we look at the world through this combinatorial lens. But I'm really interested to hear how the author takes these ideas and applies them to the actual building blocks of the universe, the particles of the standard model. I have a feeling this is where things get even more fascinating.
You're absolutely right. It's like trying to solve a cosmic jigsaw puzzle.
Yeah.
The author tries to map these principles onto the particles of the standard model.
Well, I can't wait to dive into that puzzle in the next part of our deep dive.
It's going to be quite a journey, I can promise you that.
Okay, so we've kind of laid the groundwork here. We've explored how this paper connects ancient philosophies, combinatorics, and even modulus math to paint this picture of a universe that's built on counting and cycles. But let's get down to the nitty-gritty here. How does the author apply these principles to the standard model, that ultimate guide to the fundamental particles of our universe?
Well, you got to start with that void, that ARB0 subset we were talking about.
Right.
It's not just some abstract concept. It's really the foundation for the author's whole model.
Right, because the paper argues that this void is crucial for the emergence of those mutually negating sets of particles,
Yes.
like matter and antimatter, which then go on to co-create the universe.
Oh.
But how do we get from this idea of a void to the actual particles that we observe?
The author suggests that these two fundamental sets of particles, the ones that are born from the void, are like the building blocks for everything else. It's as if that void splits into these two opposing forces, each one a mirror image of the other, each containing the potential for all the particles that we see in the standard model.
Okay, that's a pretty wild concept. So instead of protons, neutrons, and electrons being those fundamental building blocks, we have these even more fundamental particles that are generated from the void, and then they combine to create everything else.
Exactly. And the author suggests that by applying combinatorial rules to these foundational particles, it's kind of like playing with Lego blocks. You can essentially generate the entire spectrum of particles in the standard model.
That's a bold statement. It's like saying the universe is this giant combinatorial game, and the rules of the game are what determine the properties of all the particles we observe.
That's the essence of the author's hypothesis. Now, you might be thinking, okay, this sounds really cool and all, but can you actually test this theory? Can the author actually predict the properties of these particles using just combinatorics?
Yeah.
And that's where things get a little tricky. The paper doesn't give us a complete mathematical model or specific predictions that can be tested through experiments. It's more of a conceptual framework at this point.
So it's like a blueprint. It's a new way of thinking about the universe and its structure. But the details of how it all works are still being filled in.
Exactly. It's a thought-provoking idea that definitely opens up new avenues for exploration, but it's not a definitive theory yet. It needs more development. And crucially, we need ways to test its predictions against what we actually see in the real world.
Even so, the idea that something as fundamental as counting and grouping could underpin the complexity of the universe is, well, pretty mind-blowing. It challenges our assumptions about what reality is made of and how it all works.
Absolutely. It suggests that there's this deep underlying order to the universe, this hidden code that we might be able to crack if we look at it from the right perspective.
And it also kind of highlights the power of interdisciplinary thinking, right? The author's drawing on ancient philosophy, modern physics, and combinatorics to arrive at this intriguing hypothesis.
It's a good reminder that sometimes the most unexpected connections lead to those really profound discoveries.
Yeah.
By bringing together these different fields of knowledge, we gain these new insights and perspectives that we might never have even considered otherwise.
Okay, so we've got this framework where the universe emerges from emptiness, creating these two sets of particles that form the basis of everything else.
Right.
And then by using combinatorial principles, we can potentially generate that entire spectrum of particles in the standard model. But even if this turns out to be true, what are the implications? What does it change about our understanding of the universe and our place in it?
Well, for one, it suggests that the universe isn't just this random collection of particles and forces. Instead, it's this highly structured system governed by these elegant mathematical principles. It means there's a deeper level of order and predictability than we might have imagined.
So instead of just describing the universe, we might actually be able to understand the underlying code, the rules that govern its very existence.
That's the ultimate goal. And if the universe is truly combinatorial at its heart, it could have profound implications for fields beyond physics.
Like what other areas of knowledge could be impacted by this combinatorial view of the universe?
Well, think about computer science. Combinatorics is the backbone of algorithms and data structures. If the universe operates on similar principles,
Right.
it could open up totally new ways of approaching computation and information processing. We might be able to design algorithms that mimic the universe's own computational processes, leading to breakthroughs in AI and who knows what else.
That's fascinating. So instead of just using computers to simulate the universe, we might actually be able to tap into the universe's own computational power.
It's a radical idea, but definitely worth considering. And it doesn't stop there. Combinatorics plays a role in biology, chemistry, economics.
Yeah.
The potential applications are huge. It's like we're opening a door to a whole new way of understanding and interacting with the world around us.
That's what I love about these deep dives. They always leave me with more questions than answers.
Yeah.
But in the best way possible. It's like we're glimpsing this whole new landscape of knowledge.
Right.
And there's just so much more to explore.
That's the beauty of scientific inquiry.
Right.
Every answer just leads to more questions. And the more we learn, the more we realize how much we still don't know.
Right.
But it's that sense of wonder, that drive to keep exploring that keeps us going.
Before we wander too far off into the vastness of it all, I wanted to circle back to something the author mentioned that really stuck with me. The connection between modulus math, emptiness, and fullness.
Okay.
It seems to tie back to the cyclical nature of the universe.
Yes, exactly.
Yeah.
Remember how we were talking about 0 and 9 being equivalent in that base 10 modulus math?
Right.
Well, the author suggests that this mathematical equivalence might actually reflect a deeper truth about the universe.
Yeah.
They propose that 0 and 9 represent those empty and full states of creation.
So it's like the universe is constantly moving back and forth between these two states, from emptiness to fullness and back again. This whole idea of a cyclical universe expanding and contracting is just incredible to think about.
It really makes you question how we think about time, doesn't it? If the universe is cyclical, then maybe our idea of time as linear and going in only one direction is incomplete. Maybe time itself is woven into this grand cosmic dance of expansion and contraction.
Wow, that's a pretty profound thought. It makes you wonder if our universe is just one cycle in an endless series of creations and destructions, all governed by these simple, yet really profound combinatorial principles.
It's a fascinating possibility. And it raises a lot of new questions about the nature of time, the origin of the universe, and even the possibility of other universes coexisting with our own.
Okay, my head is officially spinning. We've gone from counting raindrops to reimagining the universe as this giant combinatorial machine with implications for fields beyond physics. But I have a feeling that we're only scratching the surface of this vast and complex topic.
You're absolutely right. The author's hypothesis, while fascinating, is really just the start of a much bigger conversation.
Yeah.
It's like a call to action for more exploration, for more research and experimentation, to test these ideas and see where they lead.
Well, I think we've covered a lot of ground in this part of our deep dive.
Yeah.
We've explored how the author applies combinatorial principles to the standard model, thought about the potential implications for other fields, and even touched on this mind-blowing concept of a cyclical universe.
But the journey's not over yet. In the final part of our deep dive, we'll go even deeper into the author's hypothesis,
Okay, good.
exploring some of those unanswered questions and potential avenues for future research. We'll also think about what this combinatorial view of the universe might mean for how we understand consciousness and our place in the grand scheme of things.
Sounds like we have even more mind-bending insights in store for our listeners.
Definitely. Stay tuned because it's only going to get more interesting from here.
Welcome back. We've been on quite a journey together, haven't we? Exploring this idea that the universe might be, at its core, a combinatorial marvel. We've looked at ancient philosophies, dealt with mind-bending analogies, and even took a little detour through modulus math. But now I think it's time to take a step back and think about some of the big questions that this research brings up.
Yeah, I think that's a great idea. We've covered a lot, and it's important to remember that this hypothesis, while super interesting, is still in those early stages. Like, maybe we could look for patterns in the way particles interact that line up with the combinatorial rules the author is suggesting. Or we could explore if certain properties of particles, things like their mass or charge, can be figured out using combinatorial principles.
It sounds like a whole new field of research could come out of this. A fusion of combinatorics, physics, and who knows what else.
Right.
And if this hypothesis turns out to be correct, it could revolutionize how we understand the universe.
Absolutely. You would suggest that the universe isn't just this random collection of particles and forces. Instead, it's a highly structured system, almost like a cosmic code waiting to be cracked.
It means there's a much deeper level of order and predictability than we ever thought possible.
Exactly.
Which leads me to another question I've been pondering. If the universe really is combinatorial at its heart, what does that mean for our understanding of time? Is time also a part of this combinatorial game?
Now, that's a really deep question, and one that the author brings up but doesn't really explore fully. The way we currently understand time is based mostly on this idea of a linear progression, a constant march forward from the past to the present to the future. But if the universe is fundamentally cyclical,
Right.
as this research indicates, then our whole perception of time might be off.
Right. It's like we're thinking in two dimensions when the reality might be multidimensional, with time looping and folding in on itself. This whole combinatorial view of the universe forces us to rethink some very basic assumptions, even about something like time.
For sure. And it's not just time either. This research also raises questions about the nature of consciousness itself.
Okay.
Could it be that consciousness arises from these combinatorial processes, from that really complex interplay of information and energy in the universe?
Whoa, that's taking things to a whole other level.
Right.
So instead of consciousness being this separate phenomenon, it could actually be an emergent property of the universe's combinatorial nature. It's like the universe is becoming aware of itself through this constant process of counting, grouping, and rearranging things.
It's a mind-blowing concept, for sure. It suggests that we, as conscious beings, aren't just observers of the universe,
Yeah.
but are actually integral parts of this incredible combinatorial dance.
This whole deep dive has been amazing, hasn't it? Taking us from these tiny particles to the vastness of space and everything in between.
Yeah.
And even though we're left with more questions than answers,
Yeah.
I feel like we've gained this whole new way of looking at the universe and our place within it.
That's the power of exploring new ideas,
Yeah.
pushing those boundaries of what we think we know. It's about embracing the mystery and allowing ourselves to be challenged by concepts that stretch our imagination.
And that's exactly what this research does. It reminds us that the universe is full of surprises, and sometimes those really big truths are hidden in the most unexpected places. Who would have thought that simply counting could give us clues to the deepest secrets of the cosmos?
It speaks to the way knowledge is interconnected and to the beauty and elegance of the universe itself. It reminds us that our journey of discovery is far from over. There's so much more to learn, to explore.
So as we wrap up this deep dive, what's that one key message you want to leave our listeners with?
I think the message is simple but important. Never underestimate those simple ideas. Sometimes the most profound truths are right there in front of us, waiting for us to make those unexpected connections. Keep exploring, keep asking questions, and always keep your mind open to all the possibilities that this incredible universe holds.
Well said. And to our listeners, thank you for joining us on this amazing journey. Until next time, keep those minds curious and keep exploring. Welcome to another deep dive. We're going to be exploring prion models today.
Oh, cool.
Yeah. You know, the idea that like quarks and leptons, the things we think of as the smallest building blocks of the universe,
Right.
might actually be made of even smaller pieces called prions.
Yeah, yeah. Super interesting stuff. It's like finding out that, your Lego blocks are made of even tinier Legos.
Exactly. And we're going to be looking at a specific model called the Rishon model, which uses a really kind of unique and cool approach to try and explain this.
Yeah, it uses math that's not typically used for particle physics.
Oh, really?
It uses combinatorial math.
Wow. That's really interesting. Combinatorial math, it's like the math of combinations, right?
Exactly, yeah.
Yeah.
All about counting and arranging.
So how does that apply to like the fundamental building blocks of the universe? It seems kind of like a strange connection to me.
Yeah, it is a unique approach.
Yep.
And it suggests that at some deeper level, the universe is organized according to these principles of combinations.
Mm-hmm.
So the Rishon model, it uses something called ordered pairs to represent the relationships between these fundamental building blocks.
Okay, so these ordered pairs.
Yeah.
I'm assuming they're kind of crucial to this whole model.
Yeah.
How do they work and how do they connect to these hypothetical particles called rishons?
So these pairs were written as ST, and the T represents the total number of elements you have, and the is represents how many unique combinations you can make from those elements.
Okay.
And then the Rishon model links those numbers to two hypothetical particles called the T and V Rishons.
Okay.
So the T Rishon corresponds to the T in the ordered pair, and then the V Rishon corresponds to twice the C's value.
So wait, are we saying that like the act of combining things, the very basic math of combinations could actually be like reflected in the fundamental properties of the universe?
Yeah, it's kind of a mind-blowing idea, right?
Yeah, that's
Yeah.
pretty crazy.
And one physicist, Piotr Zentikowski, suggests that these ordered pairs might even be directly related to the fabric of space and momentum.
Whoa.
Yeah, pretty intense.
So like our understanding of space-time is like not even close to complete?
Maybe not.
That's amazing. So how does this model actually like explain the existence of like specific particles, the ones we see in like experiments?
So in the Rishon model, the T and V Rishons are like the basic Lego blocks, right?
Uh-huh.
And they come together in specific arrangements called T and V groups.
Okay.
Kind of like how you'd use Lego blocks to make different structures.
Right.
And each unique arrangement of those groups represents a different particle.
So it's not just about having these like little tiny rishons floating around. It's like how they come together
Yeah, it's all about the structure.
and like interact with each other.
Exactly, exactly.
Okay.
And to kind of understand how these arrangements actually affect the properties of particles, let's look at electric charge. The Rishon model, it has a formula that explains the charge of a particle based on how its T and V groups are arranged.
Okay.
And it uses a concept called Rishon number, which is kind of like the baryon number, but specific to the Rishon model.
Got it.
It's a bit complex, but basically the idea is that the combination of T and V Rishons within a particle that determines its electric charge.
That makes sense. But one thing I've always struggled with when it comes to prion models is like the concept of mass.
Oh, yeah.
If these prions are supposed to be so tiny, how do they have any mass or energy at all?
That's a really good question, and that's a challenge for all prion models, not just the Rishon model.
Yeah.
The Rishon model proposes that maybe these T and V groups aren't actually objects in space-time, like in the traditional sense,
Okay.
but more like dimensional components of the quarks and leptons we observe.
Dimensional components. Can you break that down a little bit for me?
Yeah, sure. So imagine you have like a three-dimensional object rotating in space-time.
Okay.
As it rotates, different faces of that object will become visible to us, right?
Okay. Right.
Similarly, this model is suggesting that quarks and leptons, they might be like multidimensional objects.
Okay.
And what we see as T and V groups are just different facets of these objects as they're like rotating through this higher dimensional space.
So instead of like these tiny particles bouncing around inside a quark, it's more like the quark is like this multifaceted entity.
Exactly.
And the T and V groups are like
Yeah.
different aspects of its structure depending on how it's oriented in this like higher dimensional space.
Precisely.
Yeah.
It's a very different way of thinking about particles.
Yeah, way more abstract.
Yeah.
So how does this all like relate to the standard model of particle physics? Like, Does the Rishon model, like, agree with everything the Standard Model proposes?
So the Rishon model actually aims to reproduce all the particles of the Standard Model,
Okay.
including the symmetries and the broken symmetries.
Wow.
Pretty ambitious,
Yeah.
and it tries to kind of give a deeper explanation for why the Standard Model is structured the way it is.
So is the Rishon model like a more complete picture than the Standard Model? Does it answer all the questions that the Standard Model, like, leaves unanswered?
Well, that's where things get even more interesting. The Rishon model, at least in its current form, is what physicists would call a phenomenological accounting.
Okay.
So it's really good at describing the patterns and phenomena we observe,
Uh-huh.
but it doesn't necessarily provide like a deep mathematical framework to explain why things are the way they are.
So it's like having a detailed map of a city,
Yeah,
but not understanding, like, the urban planning principles
exactly.
that led to its layout.
That's a great analogy. We can see the structures and relationships,
Right.
but we don't fully grasp the underlying mechanisms.
So it seems like the Rishon model, while fascinating, is still very much a work in progress.
Definitely.
Yeah.
But it's important to remember that even the Standard Model has its limitations
Oh, for sure.
and its unsolved mysteries.
Right.
And the Rishon model and other Prion models, they represent attempts to kind of push those boundaries
Yeah.
and explore new ways of looking at the universe.
It's like we're trying to, like, peek behind the curtain and
Yeah.
see the machinery that makes reality tick.
Exactly. And you know, it's interesting. This model has some parallels with other Prion models,
Okay.
specifically the work of physicists like Haim Harari, Michael A. Shoup, and Nathan Seiberg.
Uh-huh.
And they've also explored this idea that quarks and leptons might be composite particles.
So there's, like, a whole community of physicists out
Yeah.
there exploring this idea.
Definitely. It's an active area of research.
That's really cool. One of the things I really liked about the source material was the interactive elements,
Oh, yeah, they're really cool.
where you could actually visualize the Rishon model because it is very abstract.
Visualizations are super helpful in physics. And the source material actually uses Feynman diagrams to illustrate how particle decays and interactions would happen within the Rishon model.
Those squiggly lines that physicists love so much.
Yes,
I
exactly.
always find them so fascinating.
They can be tricky to understand,
Yeah.
but they're a great way to represent those interactions.
Sure.
And the source material gives some really clear examples.
Okay.
It walks us through things like the decay of a boson minus or a muon, and it uses the language of T and V groups to explain it.
It's like getting a backstage pass to see how the Rishon model works in practice, not just in theory.
Exactly. It's not just equations on a chalkboard.
Right.
It's about how this model could potentially explain things we see in the real world.
Yeah, that's really neat. This has been a fascinating deep dive so far.
Yeah, it has.
We've gone from the basics of this model to, like, the complexities of how to interpret it.
Yeah.
We even touched on some philosophical implications of prion models.
It's been a great exploration.
Before we continue our deep dive into the Rishon model, let's just pause for a moment to kind of reflect on what we've learned.
Sounds good.
And we'll be back in a moment to delve deeper into the implications of this model and where it fits within the broader landscape of particle physics.
Can't wait.
Welcome back. So before the break, we were looking at how the Rishon model uses those really cool visualizations to explain how particles interact. Like, I was really struck by that example of the boson minus decay. You know, seeing how it breaks down into those T and V group components.
Yeah, the visualizations really help bring the idea to life.
Yeah.
Because at its core, the model is all about how these fundamental units, the T and V groups, combine and arrange themselves. That's what gives rise to the different properties of particles.
Right. It's like a giant cosmic puzzle where the T and V groups are the pieces, and rearranging them leads to, like,
Yes.
different particles.
Yeah. And just like a good recipe aims to replicate a certain flavor,
Mm-hmm.
the Rishon model aims to reproduce all the flavors of particles and forces described by the Standard Model.
It's a tall order.
Yeah, it is.
So we've got these T and V Rishons combining into groups, and those groups interact and rearrange themselves according to certain rules.
Right.
And those interactions are what we observe as the particles and forces in the universe. Am I getting that right?
You got it. That's a great summary.
Okay, awesome.
But it's important to remember that this model, like any scientific model, is a work in progress.
Of course. It's not like a finished thing.
Right. There are definitely still some unanswered questions and challenges.
Okay, so what are some of the big questions surrounding the Rishon model? Like, what are the things that physicists are still kind of grappling with?
One of the biggest challenges facing any prion model, really,
Mhm.
and that includes the Rishon model, is explaining the mass of particles.
Okay.
The standard model has the Higgs mechanism to explain how particles get their mass.
Right.
But how that would work within a preon model, like the Rishon model, it's still an open question.
So even though the Rishon model gives us this really cool way of looking at particle structure, we're still missing a key piece of the puzzle.
Yeah.
That whole origin of mass thing.
Exactly.
Okay.
Another challenge is that so far we haven't directly observed any preons,
Oh.
including these T and V Rishons.
Yeah, but I mean, haven't there been other particles that were theorized long before they were actually observed?
That's true. The Higgs boson is a great example.
Yeah.
It was predicted decades before it was actually detected.
Right.
But for preons, the lack of direct observation means that the Rishon model needs to make very specific predictions about what we should see in experiments if they actually exist.
It has to be testable.
Exactly. That's what really distinguishes a scientific theory from just an idea.
Right. So if the Rishon model or another preon model turned out to be correct,
Right.
what would that mean for our understanding of the universe? Like, would it change everything?
That's a really interesting question.
Yeah.
And the answer is probably yes. It would have huge implications, not just for physics,
Oh, really?
but even philosophical implications.
Like, what do you mean?
Well, if it turns out that the particles we think of as fundamental,
With the smallest thing.
yeah, are actually made of even smaller, more fundamental things, it really raises some deep questions about what it even means for something to be fundamental.
That's true.
Like, where does that chain end?
It's like those Russian nesting dolls we talked about.
Exactly.
Do we ever get the smallest one?
Right. Or does it just keep going?
Yeah, that's wild. It makes you think.
It's a huge mystery.
This deep dive has really changed the way I think about the universe.
That's awesome.
We started by looking at one specific preon model,
Right.
but it's turned into this much broader discussion about the fundamental nature of reality.
I love it. That's often how it goes with these deep dives.
Yeah.
You start with one specific thing, and it can take you to all these unexpected places.
That's the cool thing about science.
Totally.
Before we get too lost in all the existential questions, though, maybe we should bring it back to the Rishon model itself.
Right.
There's still so much more to explore.
Absolutely. Let's keep diving in.
All right, let's see where this journey takes us next.
Welcome back. We've been on quite a journey with this Rishon model. Before the break, we were talking about how if preon models are true, it really kind of changes how we think about the world.
Yeah, it really challenges our everyday experience, you know? We see things as like solid objects, but this model suggests that at the most basic level, it's all just energy and information, like a giant cosmic web of interactions.
Yeah. It's not about the individual pieces anymore. It's like how they all fit together, like the notes in a song. The individual notes matter, but it's how they're arranged that really makes the music. That's a perfect analogy. And that brings up an important point. Even if we find those ultimate building blocks of the universe, you know, like the smallest Russian doll, there's still so much complexity in how they come together and interact to create everything we see.
Right. It's mind-boggling to think about. It's almost like the search for knowledge never really ends. There's always another layer to uncover.
Absolutely. And that's what makes it so fascinating. The pursuit of understanding is a never-ending journey.
This deep dive has definitely changed the way I think about the universe. We started with this specific preon model, but it's really turned into this much bigger exploration of like the fundamental nature of reality.
That's the beauty of these deep dives. You never know where they'll take you.
So for someone listening who wants to learn more about preon models, where should they start? What resources would you recommend?
There's a ton of stuff online. A quick search for preon models or Rishon model will turn up a lot of articles, videos, even some interactive simulations like the one we talked about from the source material.
Cool. And for listeners who want to really get into the nitty-gritty, like the technical details, are there any specific books or papers you'd suggest?
For sure. If you're interested in the Rishon model specifically, check out the work of Haim Harari. He was one of the pioneers of this idea. His papers are a great starting point if you want to go deep.
Awesome. We'll make sure to link to some of those resources in the show notes. Any final thoughts before we wrap things up?
Just this. Keep exploring. Keep asking those big questions about the universe.
Yeah.
Whether the Rishon model turns out to be the answer or not, the journey of trying to understand is what it's all about.
Well said. It's been amazing exploring the Rishon model with you today. Thanks for joining us.
It was my pleasure. And to our listeners, until next time, keep those minds curious and those imaginations open. There's a whole universe out there waiting to be discovered.